Now we discuss angle modulation or exponential modulation. This includes both frequency modulation and phase modulation. The outline goes like this. We would like to start by the introduction, then quick historical notes. Then we'll focus on the concept of instantaneous frequency. We'll go into the definition of phase modulation and frequency modulation and the relation between them. And then we look at the range of possible values for Kp, which is going to be introduced, and we'll look also at the power of angle modulated signals. Now, if you try to look at the modulation in general, usually we start with a sinusoidal carrier. It has a certain amplitude shown in green and an angle shown in red. What we usually do, we try to modulate, adjust, change the amplitude and the angle, one of them or both of them, to represent the message. Now, the angle itself contains both the phase and the frequency. And this is why we're going to keep always the amplitude constant. In AM, we were representing the message in the amplitude. But now we are representing the message in the angle. And this includes both PM and FM, which stands for phase modulation and frequency modulation. So if you represent, if you modulate the message in the angle, you could get amplitude, you could get phase or frequency modulated signal. Now the example shown on the right side here, the upper one shows a signal, assuming that your message is a single tone, a sinusoid. Clearly the amplitude here represents the message. The frequency is not changing. In the lower example, the green part or the amplitude is fixed. However, the frequency changes with the message. The frequency changes with the single tone sinusoid. So it goes, the message is something like this. So when the signal is high frequency, representing high amplitude, and low frequency representing low amplitude, or vice versa. Now let's start with quick historical notes. Let's see why did people come up with FM or frequency modulation. The diagram shown here on the right hand shows you a carrier. So this is the time domain representation. And here the equivalent frequency domain representation. A carrier this is a single side, so you can see that it shows as a delta in the spectrum. Our message also is going to show as a delta. If you use double sideband amplitude modulated, the sinusoid is represented in the amplitude. You get AM, you see the double side plus the signal. In single sideband, we wanted to make the spectrum, the bandwidth less. So it covers only one band, one side of the spectrum. The idea of frequency modulation came up motivated by trying to make the spectrum even less, even smaller. How? We're going to start with a certain carrier. So the carrier in the spectrum, this is the carrier spectrum. And they thought that by changing the carrier positive and negative side to the right or to the left, here and there, we can represent the message. So this is called frequency modulated. But in the beginning, the objective was to make this variation very small to a degree that we get a very small bandwidth. This is shown in the equation here on the side. The frequency at a given instant equal to the carrier frequency plus some adjustment in the frequency. So it's K, a constant, multiplied by the message. In the beginning, they thought historically that if we make K very small, then we can make this adjustment on frequency very small. So the total bandwidth will be around the carrier frequency. We're going to go plus KMP. What's MP? Is the peak value of the message. Okay, so we go to the right here, KMP, and we go to the left, minus KMP. So what's MP? Again, it's the peak of the message assuming the message has positive and negative peak of MP. What would be the bandwidth? The bandwidth in that case is going to be from here to here, which is 2 times K times MP. Okay? And by making K smaller and smaller, the motive behind FM was to make the bandwidth smaller. It turned out that the bandwidth is not going to be smaller, and we get much more than what we started with. It's not going to be this range only. It's going to be many side lobes. So in this chapter, in this section, in this topic, we're going to understand why this is the case and what's wrong with FM requiring more bandwidth. But I just want you to understand now that the historical motive for FM turned out to be not true. The bandwidth of FM, we'll see that it's always greater than or equal to the bandwidth of an AM signal. Now let's introduce the concept of instantaneous frequency. A sinusoidal carrier with fixed frequency and phase is given by the following expression. The expression shown here, where the blue part of the signal represents the frequency and the red part represents the phase. Now, if the frequency is fixed, the relation would be linear. It's just like a straight line. The diagram shows here the sketch of the angle versus time. It looks like a straight line, and the slope is the frequency. The y-intercept is the initial phase. That's in the case of fixed frequency. But what if the frequency is not fixed? What is the frequency of the following expression? For the first term, for x1, it's relatively easy because it matches the fixed frequency format, so the frequency is 2 radians per second. And in the case of x2, we have 2t squared plus 5t plus 3. And that's not really fixed, not fixed frequency. You can see the time here is not a linear function of time. The angle is not a linear function of time. So in that case, we have to introduce the concept of instantaneous frequency, because the frequency itself here is changing with time. We cannot just take the argument of t, because t is also showing up here. So the instantaneous frequency is defined to be the derivative of the angle. Omega I stands for instantaneous. As function of time, it's equal to the derivative of the angle, and that's what we call the instantaneous frequency. Now, if the frequency is changing with time, the frequency at any instant of time equal to the slope. So it's the slope, it's changing with time. The frequency equal to the slope of the angle. That's the basic definition of the instantaneous frequency, and we'll take it further with some more examples. So the relation between phase and frequency is stated in this box. This is an important relation which we should remember. Omega I, instantaneous frequency, equal to the derivative of angle. Of course, we mean the frequency in radians per second. Now, if you want to take an example as a checkup, if we replace the angle with the case of fixed frequency, now if you take the derivative, a constant will drop out, and the derivative of this term would be omega c. So the instantaneous frequency equal to omega c if the frequency is fixed. Now we can also define the opposite. The angle equals to the integration of the instantaneous frequency. So we start at minus infinity to the variable time. We cannot repeat the variable here, so we can use a dummy variable alpha d alpha or lambda d lambda or whatever you want. So the opposite of differentiation is integration from minus infinity to the variable t in our case. Now, changing the angle of some sinusoid is the basis of 2 different types of modulation, which is the phase and frequency modulation techniques, which we are going to explain more. We have seen now that there is a relation between phase and frequency, or angle and frequency, and changing the angle in general can be used to introduce 2 types of modulations, which is frequency and phase modulation. Now we are ready to introduce phase modulation, PM. If we adjust the phase of the carrier to represent the message, as we can see here, we get what we call the phase modulation. So the phase of the carrier is directly proportional to the message, and this is why we call it phase modulated signal, because this part, which is the phase, is proportional to the message. Now we add a constant, proportionality constant Kp. Why do we add this? Because we want to control how much phase change is there. If we make Kp large, it means the sensitivity to the message will be larger. We can make it even small. Remember now that A is constant, it's not amplitude modulated. Omega C is also constant. So the angle for this expression, is what is inside the bracket here. This is called the angle. This is theta in green. It's equal to omega ct plus kpmt. And the instantaneous frequency is the derivative of the angle. If you differentiate the angle, you get omega c plus kp times the derivative of the message, which we refer to as m dot. The angle is proportional, the phase is proportional to the message, we call it phase modulated. However, the frequency here is proportional to the derivative of the message. And this is why we don't call it frequency modulated, because the frequency is not directly proportional to the message, but rather to the derivative of the message. Okay, so in this slide, I would like you to remember this formula, which is the basic definition of phase modulated signal. Similarly, we can introduce the frequency modulation. Now we need to do a small trick. How do we define FM? We will start with, of course, the amplitude will be constant. We'll start with changing the phase with the integration of the message. So it's A cosine omega ct plus kf. Now we use subscript f to represent frequency. And now we multiply not by the message, by the integration. Why? Because we know now, if you get the angle and the instantaneous frequency, the angle is this term here. It's what's inside the bracket, we call it the angle. If you want the frequency, the instantaneous frequency, you differentiate the angle. So we get omega c from here. From here we get kf, it's just a constant, times the message. Now we can see that when the phase is proportional to the integration of the message, then we get the instantaneous frequency to be proportional to the message, and this is why we call it frequency modulated signal. Once more, very important to remember the general form for the FM signal. The major difference, then now we call this kf instead of kp, and we are multiplying by the integration of the message. Sometimes we call this A of t. So A of t is a standard notation to represent the integration of m of t. Now we see that there is a strong relation between FM and PM. Look at the two expressions here. We can see here that there is a tight relation between the two. They are tightly related. If we come to the PM expression and we replace the message by its integration, you get an FM signal. Similarly, if you go to the other expression, to the FM expression, and you replace the message by the derivative of the message, the derivative will cancel with the integration, and you get a PM signal. Using this fact, I can use an FM modulator to generate PM signal and vice versa. Look at this block diagram. What we have here is a phase modulator. If you give the message, you give the PM. If we add an integrator before that, then the integrator plus a phase modulator are equivalent to a phase modulator. So if you start with the message, you integrate, use PM modulator, you get FM signal. Similarly, if you want to build a PM modulator, you can start with FM modulator, but now we need to add the derivative because the integration is already inside the phase modulator. The differentiation with the integration will cancel, and the message will give you a PM, the message at the input will result in a phase modulated signal. Okay, so you should be able to manipulate phase and frequency modulators. Now here are a few notes about PM and FM and their relation. First, FM and PM are indistinguishable, which means if you look at the modulated signal, you cannot tell whether it is FM or PM. If I just go back to this example, we have M of t and its integration A of t. And then you see a modulated signal. This signal, is it PM or FM? Okay. This signal could be FM for A of t, and it also could be a PM of A of t. We cannot tell exactly. Just looking at an analog signal, modulated signal, we cannot tell whether it's FM or PM, because as you have seen the equation, they are directly related. PM and FM are two examples of the more general angle modulated form. You can have combined FM and PM. We have just looked at FM and PM. You can change the angle in general. I just would like to warn you that we started assuming that the bandwidth of FM is going to be 2 kF times MB. 2 because we are changing on the right and left. We're increasing the frequency, decreasing the frequency. MP is the peak of the message. KF is the proportionality constant. And similarly for PM, the difference was we have different constant and we have MP dot, the max. By the way, MP dot is the derivative, the peak of the derivative. Okay, it's not the derivative of MB. You take the message M of t, you differentiate. So you take M, you get from M of t, we get the derivative M dot, and then we find its peak. The peak of this is called MP dot. Now, those assumptions about the bandwidth, we'll find out that they are not correct. So please do not use this as bandwidth. These are just called frequency deviation. We'll see why in detailed presentations. Now, once more, we have started FM and PM with the objective of reducing bandwidth, but this is not true. I just want to also hint that in most cases, PM performs better than FM, especially when we look at digital communication. But the details of how this works is beyond the scope. So PM and FM, if you want to study their performance, we need noise background and statistical analysis, which is beyond the scope of this course. But just for your information, PM performs better under some conditions than FM signals. Alright, here are a few comments about the range of values for Kp. In phase modulated signal, you have to make sure that Kp times M of t is limited between minus pi or minus 180 degrees, okay, minus 180 degree to plus 180 degree. Okay, why? Because there will be some ambiguity. Let's explain this with an example. Now, I'm just sharing with you here that I just chose the Kp to be 3 pi over 2, and the message can take different values. So what if the message equal to 1, or if the message equal to minus 1/3? If the message equal to 1, then if the message equal to 1, you get 3 pi over 2. That's like 270 degrees. Similarly, if the message equal to minus 1/3, and if you substitute, you get minus pi over 2. Minus pi over 2 is again minus 90 degrees, which is the same angle here. So different messages results in the same angle. This is something, of course, we don't want to do, because at the receiver we want to convert back from angle to message, and there will be ambiguity. Was it 1/3, minus 1/3, or was it 1? Remember that for angles, adding multiples of 2 pi get you back to the same angle. So we have to be careful about the choice of Kp. So first, if there is discontinuity in M of t, then Kp times M of t should be restricted. And this is usually in digital communication. If M of t is continuous, then there is no need for the restriction because the change is gradual. So we can look at the previous angle to tell whether it's minus 90 or 270, or we can look at the previous angles because it's gradual change. And of course, for real M of t, they are band limited, so there is no real discontinuities. So there is no strong restriction on Kp. Theoretically there is, but if in practice there isn't. And we conclude by the following comment that KB is usually a small value because KB is multiplied by the message. If you compare it with KF, which is multiplied by m dot, the derivative of the message, then the derivative would be much larger value. So KB is usually a small value. Now, power of angle modulated signals. The power of angle modulated signal luckily is simple. You can see the two expressions. The angle itself does not contribute to the power, so all of this is not a problem. In both cases, the power would be amplitude squared over 2. So PM or FM has the advantage of having constant power irrespective of the message, and that is A squared over 2, regardless of KP, regardless of KF, regardless of the message or its integration. This is considered one advantage for angle modulation because the power is independent of the message. We'll see some more examples about how to sketch FM and PM signals.